All right, so let's get started with preparing for the machine learning group I'm in. So I want to do one more video on um, lesson 3 before moving on to lesson 4. That video is just going to be finishing up those questions. So let's go into my Google Drive for my other account. Okay, and now we should have, yep, so we have questions here. We have questions for lesson 2, and then we also have questions for lesson 3, and you can see that I didn't answer all of the questions. I stopped at question 15. So I would like to pull up the book and answer all those questions and then stop the video, upload it as a part 3 for lesson 3, and then start a new video for lesson 4. Okay, so let me do that. The first step in doing that is pulling up the book. Okay, because this is what will be used to find the answers to these questions. The next step is going to be reading the question. How is a grayscale image represented on a computer? What about a color image? So I think that's in chapter 4. There might be some stuff in chapter 2 as well. But let's search for gray and see if anything pops up. Or scale. So we do see that the answer will be here somehow. The question has been asked here. So the answer is hopefully here as well. Okay, so let's begin. The first step is to consider how images are represented on a computer. Pixels, the foundations of computer vision. In order to understand what happens for a computer vision model, we first have to understand how computers handle images. We'll use one of the most famous data sets in computer vision, MNIST, for our experiments. MNIST contains images of handwritten digits collected by the National Institute of Standards and Technology and collated into a machine learning dataset by Yann LeCun and his colleagues. LeCun used MNIST in 1998 in LeNet-5, the first computer system to demonstrate practically useful recognition of handwritten digit sequences. This was one of the most important breakthroughs in the history of AI. Okay, let's take a look at this thing. I'm guessing it's going to be like a big machine that takes up a room. Or, well, in 1994, probably not. Looks like it's just software, actually. Yeah. Alright, so that unfortunately didn't answer the question about a grayscale image. So, yeah, I'd like to kind of just get on with this and get this done as soon as possible. Okay, so I can't see where it's talking about a color image. So answering the second part of the question will... Oh. You know what? I'm almost tempted to just read this whole thing. It probably wouldn't take super long to do that, and I would definitely know the answers. I mean, I'm going to need to answer all of the questions anyway. So, yeah, it actually looks like this is further down because this is actually like the 15th question. So, I might not need to read everything, but maybe if I just read um, starting at the answer to the 15th question. Uh, Yeah, you know what? This is a really complicated technical chapter. So let's just read the whole thing. Hopefully, it won't take more than an hour to do that. I'm kind of hoping this video will be less than 2 hours, um, so that I can have this afternoon from 1 to hopefully like 5 or 6 at the latest to finish up the next lesson. Okay, so we're just going to read everything in this book and hopefully everything in this chapter, and then hopefully that will be enough to answer the questions and move on to the next lesson. So, under the hood, training a digit classifier. Having seen what it looks like to actually train a variety of models in Chapter 2, let's now look under the hood and see exactly what's going on. We'll start by using computer vision to introduce fundamental tools and concepts for deep learning. To be exact, we'll discuss the roles of arrays and tensors and of broadcasting, a powerful technique for using them expressively. We'll explain stochastic gradient descent, SGD, the mechanism for learning by updating weights automatically. We'll discuss the choice of a loss function for our basic classification task and the role of mini batches. We'll also describe the math that a basic neural network is actually doing. Finally, we'll put all these pieces together. In future chapters, we'll do deep dives into other applications as well and see how these concepts and tools generalize. But this chapter is about laying foundation stones. To be frank, that also makes this one of the hardest chapters because of how these concepts all depend on each other. Like an arc, all the stones need to be in place for the structure to stay up. Also, like an arc, once that happens, it's a powerful structure that can support other things, but it requires some patience to assemble. Let's begin. The first step is to consider how images are represented in a computer. Okay, so yep, if there's one chapter to read word for word every way through, it sounds like it's this one. I'm going to make sure I have enough space on my hard disk to save this video. So I'm going to delete, I already uploaded my, I think, I might not have. If I didn't, let me just take a look and see if I uploaded everything for my, okay, network. Oh. Okay, so, it looks like I've got video 3 uploaded, so let's take a look and see which, yeah, let's see which video I left off on last time. Okay, so it looks like I have not made a video 4 yet, so everything is uploaded. So yeah, unfortunately my disk space on my computer is a bit small. I'm probably due for a new computer eventually, but I'm pretty happy with, well, in some sense I'm happy with the one I have. It's a Dell Inspiron. Like, I wanted to keep my costs down when I bought it. And I'm pretty happy with it, but it is definitely a cost-saving computer, that's for sure. So the hard disk is kind of small. It's a little bit clunkier, but I'm pretty happy with it. Alright, so let's keep reading this chapter. The goal is to read all of chapter 2, and hopefully by the end of that I'll have more than enough information to answer all of the questions. Okay, so all of chapter 4. Pixels, the foundations of computer vision. In order to understand what happens in a computer vision model, we first have to understand how computers handle images. We'll use one of the most famous data sets in computer vision, MNIST, for our experiments. MNIST contains images of handwritten digits collected by the National Institute of Standards and Technology and collated into a machine learning dataset by Jan LeCun and his colleagues. LeCun used MNIST in 1998 in LeNet-5, the first computer system to demonstrate practically useful recognition of handwritten digit sequences. This was one of the most important breakthroughs in the history of AI. Okay, so I need some water. I'm dying here, so we're gonna read down to end sidebar, and we're gonna get some water and come back. Sidebar, tenacity and deep learning. The story of deep learning is one of tenacity and grit by a handful of dedicated researchers. After early hopes and hype, neural networks went out of favor in the 1990s and 200s, and just a handful of researchers kept trying to make them work well. 3 of them, Jan LeCun, Yoshua Banigo, and Geoffrey Hinton, were awarded the highest honor in computer science, the Turing Award, generally considered the Nobel Prize of Computer Science. In 2018, after triumphing despite the deep skepticism and disinterest of the wider machine learning and statistics community, Geoff Hinton has told of how even academic papers showing dramatically better results than anything previously published would be rejected by top journals and conferences just because they used a neural network. Jan LeCun's work on computational neural networks, which we will study in the next chapter, showed that these models could read handwritten text, something that had never been achieved before. However, his breakthrough was ignored by most researchers, even as it was used commercially to read 10% of the checks in the US. See, that's what I thought. Like I remember, I kind of remember when I was a kid, like learning that the post office actually, in their expensive machines, and it actually pains me to say, but I kind of feel that, well, anyways, the post office uses AI to read their letters, and that was always something I found really interesting, is that AI is actually more commonplace and serves a bigger purpose in our society than we could ever imagine. And not only is it doing it now, it was doing it for decades. I mean, right there it says his breakthrough was ignored by most researchers, even as it was used commercially to read 10% of checks in the USA. Like this is from a long time ago. I mean, look at this. This is from the 1990s to 2000s. So when I was young, would be right in this area. So yeah, to learn that the post office uses AI, it's very likely. I mean, let's just look it up. Post office AI. Yeah, so right here. Yeah, so it looks like they've expanded it more than just reading letters and envelopes. Um, they're actually using it to track missing packages. It looks like you can just, instead of working with somebody to find your package, you can just talk to the AI and it knows exactly. It can serve you better. It's just a person. They would be looking at an AI anyway because they'd be looking at like a data set of but so. Yeah, so that's something I think a lot of people don't think of when they think of AI, is something like the post office and reading your letters. I mean, you think somebody's taking your letter and just looking at it like this and then like putting it, like, no, it just goes through a machine and it gets read automatically by an AI. Yeah, so really interesting. I think well, I wanna keep going on this book. This is my goal. So let's stick to the plan here. So in addition to these three Turing Award winners, there are many other researchers who have battled to get us to where we are today. For instance, oh no, not John, Jürgen Schmidhuber, who many believe should have shared, yeah, what the hell, he got screwed, who many believe should have shared in the Turing Award, pioneered many important ideas, including working with his student Sepp Hochreiter on the long short-term memory LSTM architecture, widely used for speech recognition and other text modeling tasks, and used in the IMDb example in Chevron. There is a lesson here for all of us. On your deep learning journey, you will face many obstacles, both technical and even more difficult, posed by people around you who don't believe you'll be successful. Oh man. That's basically the crux. That's why it's important to be able to like, I mean, one advice I would have for anyone watching this, um, for dealing with people around you who don't believe you'll be successful, is kind of don't frame them as an adversary. Like, don't think of that person as somebody who's not believing that you'll be successful because they don't want you to succeed. Frame them as somebody who doesn't believe you'll be successful because they have something valuable to contribute to you. So, just ask them questions. Why don't you think this will be successful? Why, and some really valid things might come up that you hadn't considered. And, have a discussion, have an adult discussion with this person. Don't accuse them of trying to, you know, derail you or whatever. Respect this person as a fellow peer and professional, and if you don't understand why they are posing a challenge, ask them, why is this difficult? Why is this something that what problems do you think I will encounter in pursuing this? Um, and yeah. And if it just so happens you can't make the case, it's like, yeah, this is going to take me a long time of dedicated, serious work, and I could be doing other things, and you know the benefits of this are this and this and this, but um, you know the challenges are this and this and this, and oh, you know, I never thought of this, so thank you for that. So you know it might, you know, ideas in my mind aren't really sacred. Like they're like an idea isn't as important as a result. Like the results are like far more important than the ideas. And if you have an idea that, you know, it doesn't matter if you have the best, like the best, like isn't as important in my mind as the thing that actually happens. I mean, you want the thing that actually happens to be as good as it can possibly happen, of course, but having that thing be the absolute best way you can imagine it to be is just not possible because you're imagining it from one perspective. There's other people imagining different things, and you're going to need to accommodate those views in order to rely upon people and you know have that, because I mean unless you can do it 100% by yourself in a vacuum with no help at all, um, you know it's not your thing. Like it's a shared thing. People are helping you make it happen, so you really got to respect their professional opinions, and it just makes it better too in my mind. It's, you know, a lot of people kind of think now, especially nowadays, that compromise is about making something worse. But in my mind, like compromise is about making something better. Because like, you know, there just might be a valid reason that my idea or design or something is not ideal. Like there might be some constraint I hadn't thought of or that I wasn't kind of told initially because people didn't know it existed initially. And you know, it's about making something that's valuable and that has a, you know, that people want. You know, it's not about just forcing something to happen one particular way because one particular person believes that to be the best way. I mean, it's like if you're going to be the only person in the world who ever uses that idea, like, okay, yeah, like you can you can cut out, you know, other opinions, but you know, if other people are going to use it, like, come on, like, you expect them to want to use it exactly the way you want to use it, like. But okay, that's kind of a tangent, but I think most people in tech can really speak to this, and I just wanted to give my opinion about that because I think it's served me pretty well throughout my professional career so far. There's one guaranteed way to fail, and that's to stop trying. We've seen that the only consistent trait amongst every Fast.ai student that's gone on to be a world-class practitioner is that they are all very tenacious. Alright, so I gotta take a pause here to get some more water. I'm like dying, my throat is the Sahara Desert right now. So I'll be back real shortly. Okay, so it's red now. I am recording. I gotta check that carefully every time because I made that mistake once. So next section is gonna be end sidebar. For this initial tutorial, we are just going to try to create a model that can classify any image as a 3 or a 7. So let's download a sample of MNIST that contains images of just these digits. Okay, so I believe I did that. Yeah, I did that already last time in the video, like all that. So I'm not going to do that again. I guess one thing I could do that would be interesting would try to do this with like a 6 and a 9, of course, or some other digits besides 3 and a 7. I think that could make it interesting for me. So I'm going to do that actually. Let me start my paper space, and then we'll keep reading, but I'll come back to it and run the examples using the digits 6 and 9, as are the most logical digits to use. Okay, so this is going to take like 5 minutes. All right. We can see what's in this directory by using ls, a method added by FastAI. This method returns an object of a special FastAI class called L, which has all the same functionality of Python's built-in list, plus a lot more. One of its handy features is that when printed, it displays the count of items before listing the items themselves. If there are more than 10 items, it just shows the first few, path.ls. Okay, so this is just a way to look at the directory. We can also use the GUI in Paperspace to see the same sorts of files. Here's a file that should look really familiar. The MNIST dataset follows a common layout for machine learning datasets. Separate folders for the training set and the validation set and or test set. Let's see what's inside the training data. There's a folder of 3s and a folder of 7s. In machine learning parlance, we say that 3 and 7 are the labels or targets in this dataset. Let's take a look at one of these folders using sorted to ensure we all get the same order of files. Okay, so I'm not sure what this. Oh, you know what? I think the different kinds of, because this is just a database of many people writing the digit 3. So here's the. I guess I'm surprised that this is the 10th one. I guess let's see here. Well, no, I'm surprised that it's the 10th digit. I would think, or the 10th image. I would think it'd be the 3rd image if you have an image for each of the numbers. Either that or the 29th image, because you'd have all of the alpha, if it's alphanumeric A through Z and 1 through 3. We'll be able to look at this training set later though. As we might expect, it's full of image files. Let's take a look at one now. Here's an image of handwritten number 3 taken from the famous MNIST dataset of handwritten numbers. Here we are using the image class of the Python imaging that really hurt, library. Oh my god, that really hurt. I bashed my knee on the desk. Which is the most widely used Python package for opening, manipulating, and viewing images. Jupyter knows about PIL images, so it displays the image for us automatically. What is a PIL image, and why did that hurt? Like, because I banged my knee against the desk before and it hasn't hurt that bad. In a computer, everything is represented as a number. To view the numbers that make up this image, we have to convert it to a NumPy array or a PyTorch tensor. For instance, here's what a section of the image looks like converted to a NumPy array. Okay, so, and now remember, this is just a small section of the image. It'd be nice to, okay, well, anyways. The 4:10 indicates that we requested the rows from index 4 included to 10 not included, and the name for the columns. NumPy indexes from top to bottom and left to right. So this section is located in the top left corner of the image. Here's the same thing as a PyTorch tensor. We can slice the array to pick just the part with the top of the digit in it, and then use a pandas data frame to color code the values using a gradient, which shows us clearly how the image is created from the pixel values. Okay, so maybe some of these questions are ready to be answered now. Okay, I don't see anything yet. You can see that the background white pixels are stored as the number 0, black is the number 255, and shades of gray between the two. The entire, so I think this is the answer. This is the answer to that. So perfect. Now we just gotta find the answer to how a color image is represented on a computer. But a grayscale image, oops, if I may please, yeah, for a grayscale image, the background white pixels are showed as the number 0, black is the number 255, and shades of gray are between the two. The entire image contains 28 pixels across and 28 pixels down, for a total of 784 pixels. This is much smaller than an image that you would get from a phone camera, which has millions of pixels, but is a convenient size for our initial learning and experiments. We will build up to bigger full color images soon. So now you've seen what an image looks like to a computer. Let's recall our goal. Create a model that can recognize 3s and 7s. How might you go about getting a computer to do that? Warning, stop and think. Before you read on, take a moment to think about how a computer might be able to recognize these two different digits. What kinds of features might it be able to look at? How might it be able to identify these features? How could it combine them together? Learning works best when you try to solve problems yourself rather than just reading somebody else's answers. So step away from this book for a few minutes, grab a piece of paper and pen, and jot some ideas down. God damn it. See, this sort of thing, like, okay, yeah, I get it. Like, learning, yeah, like, and I agree, yes, you've got to figure it out yourself. You got to think about it. You can't just, you know, shove the information in your eyeballs. You've got to think about it yourself. But at the same time, like, I don't know, like, I'm not at this level. Like, I haven't done calculus since I was in high school, pretty much. I guess I learned it on my own a little bit, but when I did that, like I just don't feel like I'm at the level to just sit and think about Turing Award-winning machine learning and come up with my own answers. All right, so let's keep reading. So first try pixel singularity. So here's a first idea. How about we find the average pixel value for every pixel of the 3s, then do the same for the 7s. This will give us two group averages, defining what we might call the ideal 3 and 7. Then, to classify an image as one digit or another, we see which of these two ideal digits the image is most similar to. This certainly seems like it should be better than nothing, so it will make a good baseline. See, I'm just not sure I could have thought about that. Like, I think the person who thought of that is, like, really, really smart. And, like, I should be kind to myself, charitable to myself. I'm smart, I'll say it. But am I gonna win the Turing Award for computer science? Probably not. Jargon, baseline. A simple model which you are confident should perform reasonably well. It should be very simple to implement and very easy to test, so that you can then test each of your improved ideas and make sure they are always better than your baseline without starting with a sensible baseline. It is very difficult to know whether your super fancy models are actually any good. One good approach to creating a baseline is doing what we have done here. Think of a simple, easy to implement model. Another good approach is to search around to find other people that have solved similar problems to yours and download and run their code on your dataset. Ideally, try both of these. Step 1 for our simple model is to get the average of pixel values for each of our two groups. In the process of doing this, we will learn a lot of neat Python numeric programming tricks. Let's create a tensor containing all of our 3's stacked together. We already know how to create a tensor containing a single image. To create a tensor containing all the images in a directory, we will first use a Python list comprehension to create a plain list of the single image tensors. We will use Jupyter to do some little checks of our work along the way, in this case making sure that the number of returned items seems reasonable. Okay. Note, list comprehensions. List and dictionary comprehensions are a wonderful feature of Python. Many Python programmers use them every day, including the authors of this book. They are a part of idiomatic Python, but programmers coming from other languages may have never seen them before. There are a lot of great tutorials just a web search away, so we won't spend a long time discussing them now. Here is a quick explanation and example to get you started. A list comprehension looks like this. New list equals bracket f parentheses O end parentheses for O in a list if like that thing. This will return every element of a underscore list that is greater than 0 after passing it to the function f. There are 3 parts here: the collection you are iterating over, a list, the optional filter, if O is greater than 0, and something to do with each element, f function of 0. It's not only shorter to write, but way faster than alternative ways of creating the same list with a loop. So yeah, I understand this pretty well, so I'm going to explain it in a way I think hopefully will be better than how the book just explained it. So I think a good way to explain it is we've got a list comprehension right here, and I'll make this as big as possible. So the book did a good job of explaining it, I think, but it just might not be intuitive from what was in there. So the thing that I think will make a list comprehension more intuitive will be understanding that it is a collection of different parts. So it'd be great if I could, yeah, okay. Well, let's use an underline. So we're gonna use a line here, and we're gonna have we're gonna use this blue, this purple, and this oh, this is purple. What color is this? Indigo. Okay, so we'll use turquoise, indigo, and purple, and we'll underline different parts of this. So one thing you'll notice is, first of all, that indigo and turquoise are too close together. I can't tell the difference, so we'll use red here. But one thing you'll notice is that I only added 2 underlines. That's because in this particular list comprehension, we've only got 2 parts. You can add a third part to list comprehensions. Let me do, so now notice we have O here. So for O in sevens, so we have sevens is our list. So it's a list comprehension because we're doing something, we're iterating over a list, and then not only that, we're creating a new list for each iteration in that. So something on this side here, in the blue underline, we're doing something with this O. Then of course you're always going to have your loop, but let's say for thing in a list so we're going to say print thing in a list for thing in a list in my list if thing in a list equals apple. Okay, so let's think more about this. First, let's underline the parts. So this is kind of I'm going to do what the book did and say try to do this on your own. Pause the video. Well, I'm going to make this cleaner for you here. Yeah. So for thing in my list, if thing equals apple. So take this moment, pause the video, and see if you can do this underlining exercise here, and come up with the parts. And I did miss the brackets on the end. So there should be brackets. Yeah. So I'll just add the. So that's not going to work. Delete. Okay. Well. Okay. Sweet. Okay. So now I can move. Yep, I can move this over. Yep, and now I can add the missing brackets. Okay, so now, yep, now the other bracket, perfect, okay. So here's my list comprehension. So pause the video and add the underlines. Okay, so hopefully you're back. I'm gonna give the answer. So if you said that the equivalent part of this is gonna be here, congratulations, that is the freebie. You got the easy one. You're paying attention at the most minimum level. Now if you said the second section, oops, and I want to keep the colors the same. There we go. So if you said the second section was all of this, well, you got it wrong. It's going to be just through here. So remember when I said that this was missing a third section? So the third section is going to be this if statement here. So we can leave out this section here. It's just optional. It's just if you don't want everything. So let's put that into code and kind of understand a bit stronger what that means. So I'll open a terminal here. Perfect. And then I'll do pi-3-m IPython, just because I like that interpreter shell better. Okay, so now let's try on that. So we're gonna do test, and the font is horrible. So if I just do that, you can see we get a result, and that is a dictionary with one element in it, and the element is test. So let's say example equals test. So type on example, it's a list. Length on example, one thing is in the list. Okay, so let's make a list right now. It's going to be called my list. Okay, so here is a list. It's got nothing in it. So sure enough, that's going to be, it actually might be a none type. Nope, it is a list. Yep, and then the length, it just doesn't have anything in it. But we can redefine it to have things in it. So let's have a banana, let's have some cabbage in there. We're probably gonna need some B12. And then, oh, iodide as well. So let's add a seaweed vegetable. Okay. Okay, that will so like a like some nori or some of the wrappings around some sushi. Just cut that up and add it to something, and you have got enough iodide. Otherwise, if you're having yeah, broccoli. If you have broccoli and stuff without that, it has a compound called something that can cause goiters, especially on your thyroid. So you gotta have, like, even if you're not vegan or vegetarian, you gotta have enough iodide. But salt is fortified with iodide usually, unless you buy non-iodized salt. But if you don't want to have extra salt due to high blood pressure, you can just have seaweed vegetables, and they have like so much iodide in them. You actually have to be a bit careful and not eat too much of them. Okay, but then we'll add 3 apples in here. Okay, so now we can do print thing for thing in my list. So you can see what we did is we printed thing. So for thing in my list, so we're just going to say, so thing is just a placeholder for each element. So we went through, we printed everything, perfect. Now, one interesting thing that happened is we got back a new list, and it said none in them all. That's because if I do example equals print and then test. So we printed out the word test, but if I do a type on example, you can see I got a none type back. That's because the print function, if we do a help on print, it doesn't return anything. It's not a fruitful function. So if I were to define a function, my func, and I were to say print hello world, and then that's all there is to it. The return in functions in Python is implicit. I'll just add it explicitly, but you can see I'm not adding anything extra after the return. There's nothing there. So if I do func, it prints hello world, but if I do example equals my func, we get hello world again, but example is a none type. Now, if instead of that, I were to do
my func return print hello world, now we've got something that is called a fruitful function. It produces something back. Instead of just doing what you told the function to do, it also provides something for you to use later. Whereas a fruitless function, we saw with the return blank, we got that none type back when we saved the function into a variable. So let's see what we get now that it's a fruitful function. So we get the exact same thing, hello world. So let's try saving the function output into a variable. Same thing, we get hello world, but now if I do a type on example, it's still a none type. What the hell? Oh, no, I know why it's a none type. It's a none type because print hello world is a none type. So I basically said return a none type. So this is basically what I meant. Yeah, this is what I meant. But if I do that, it's oh, there we go. So yeah, and now it's going to return that, and now it's a fruitful function because it doesn't return that none type. So now if I do a type on example, it's going to be string, and example is going to be hello world. So hopefully that makes sense, and I didn't just make everything super confusing. But let's try this again. We're going to do, but instead of doing print, we're going to do thing for thing in my list. And you can see now we've got back just a dictionary, and we don't have the nuns because print returns a none type. Another thing we can do is now you can get really weird, and you can do my func for thing in my list and not even use thing at all. I don't know why you would ever want to do that, but of course I just get back hello worlds. I guess if you just wanted to have a function trigger for each entry in the list, but not you just wanted the number of times the function triggered to be based on the number of entries in your list, but not based on any specifics within that list. That could be something you would want to do. And then, like an example, you can say if thing equals apple. So now it's only going to trigger 3 times because apple is only in the list 3 times. So I could see that being really useful because, like, for example, I'm a network engineer by day, so you could take a show run, you could do a special function of things you want to happen every time there's a shutdown command in the show run. You want to go and no shut everything. A list comprehension could help you do that faster and easier. Okay, but that's the end of that. That was a huge tangent. And hopefully it didn't just make everything more difficult for everyone to understand. We'll also check that one of the images looks okay, since we have tensors, which Jupyter by default will print as values, rather than PIL images, which Jupyter by default will display as images. We need to use FastAI's showImage function to display it. For every pixel position, we want to compute the average over all the images of the intensity of that pixel. To do this, we first combine all the images in this list into a single 3-dimensional tensor. The most common way to describe such a tensor is to call it a rank 3 tensor. Okay, so what is a rank 3 tensor? It's a combination of all the images into a single so it's a single three-dimensional. Okay, well, I'll just include this verbatim just because I want to move on. Okay, so I don't know what the answers are for those other things. I think the book just wasn't very clear on that. But I mean, I can think about it and write down my own answer, and if the answer's wrong, then so be it. So, I mean, I would assume that they would just use more bits. Because 255, that's 8 bit. Just use more bits to represent more values. Yeah, so that's probably the right answer. Yep, and then how are the files and folders structured? Why? I don't know. That's not something I think was shown. Oops, I am gonna need to take a quick break. Oops, and I lost. Unfortunately looks like I lost where I was last time. Oh, I think I was right here. Yeah. Oh, yep. So, yep. We'll often need to stack up individual tensors in a collection into a single tensor. Unsurprisingly, PyTorch comes with a function called stack that we can use for this purpose. Some operations in PyTorch, such as taking a mean, require us to task our integer types to float types. Since we'll be needing this later, we'll also cast our stacked tensor to float now. Casting in PyTorch is as simple as typing the name of the type you wish to cast to and treating it as a method. Generally, when images are floats, the pixel values are expected to be between 0 and 1, so we will also divide by 255 here. Perhaps the most important attribute of a tensor is its shape. This tells you the length of each axis. In this case, we can see that we have 6,131 images and each of the 28 by 28 pixels. Each of size 28 by 28 pixels. There is nothing specifically about this tensor that says that the first axis is the number of images, the second is the height, and the third is the width. The semantics of a tensor are entirely up to us and how we construct it. As far as PyTorch is concerned, it is just a bunch of numbers in memory. The length of the tensor's shape is its rank. Okay, so I think I have the answer to this. How are the files and folders? Okay, I don't have the answer to this. I'm just gonna maybe on the forum or Google, because I mean personally I just want to know before I'm reading on, because oh, here we go. Yeah. Ah, perfect. So there are two directories, train and valid, which each contain two directories, 3 and 7. Inside those directories are images of the respective digit. The train directory contains the majority of images to be used to train a model. Likewise, the valid directory contains images to validate a model. There's also a labels.csv file, which likely contains a mapping between file names and digit label. Perfect. I'll be leaving that open because that's just a better answer than was in the book or I could have thought of myself. I understand the file structure a lot more clear now. They're nested within each other, so you get your training set, you get your validation set, and then within each you have a directory for each digit with multiple images for the digit. So that makes sense to me, but just thinking of that is not is not going to be time efficient for me. I've only got a limited amount of time today. Okay, so there's nothing specifically about this tensor. Okay, yep, I remember that. So let's let's read down to the, because it's going to be clear that I stopped at the blurry 3. Okay. It is the length of a tensor's shape is its rank. It is really important for you to commit to memory and practice these bits of tensor jargon. Rank is the number of axes or dimensions in a tensor. Shape is the size of each axis of a tensor. Is it axis or axis? I guess I'm used to the word chassis looking weird, but I'm pretty sure it's axis. My brain is like not working.
Axis.
Yeah, okay, it's axis. Okay, so A, what does the A stand for? Oh, it's a jargon word? Okay, so is a jargon word? Watch out, because the term dimension is sometimes used in two ways. Consider that we live in a three-dimensional space where a physical position can be described by a 3-vector v. But according to PyTorch, the attribute v ndim, which sure looks like the number of dimensions of v equals 1, not 3. Why? Because v is a vector, which is a tensor of rank 1, meaning that it has only one axis, even if that axis has a length of 3. In other words, sometimes dimension is used for the size of an axis. Space is 3-dimensional. Other times it is used for the rank or the number of axes. A matrix has 2 dimensions. When confused, I find it helpful to translate all statements into terms of rank, axis, and length, which are unambiguous terms. We can also get a tensor's rank directly with NDIM. Finally, we can compute what the ideal 3 looks like. We calculate the mean of all the image tensors by taking the mean along dimension 0 of our stacked rank 3 tensor. This is the dimension that indexes over all the images. In other words, for every pixel position, this will compute the average of that pixel over all images. The result will be one value for every pixel position or a single image. Here it is. Okay, so that's the blurry 3. Let's stop after that because it's just, I guess I could read down there and then I would have less to go later if I did that. I'm going to do that because I want to have less to read later, so I'm going to read more now and take my break a little later. According to this data set, this is the ideal number 3. You may not like it, but this is what peak number 3 performance looks like. You can see how it's very dark, where all the images agree it should be dark, but becomes wispy and blurry where the images disagree. Let's do the same thing for the 7s, but put all steps together at once to save some time. Now pick an arbitrary 3 and measure its distance from our ideal digits. Stop and think. How would you calculate how similar a particular image is to our ideal digits? Remember to step away from this book and jot down some ideas before you move on. Research shows that recall and understanding and not having large trucks make huge noises outside your window.
improves dramatically unless they're delivering a package I'm waiting for. Am I waiting for a package? I don't even think so. When you are engaged with the learning process while you're solving problems, experimenting, and trying new ideas yourself. Actually, I am waiting for a package, but I got no indication that it would be delivered today. Here is a sample 3. How can we determine its distance from our ideal 3? We can't just add up the differences between the pixels of this image and the ideal digit. Some differences will be positive while others will be negative, and these differences will cancel out, resulting in a situation where an image is too dark in some places and too light in others, might not be shown as having 0 total differences from the ideal. This would be misleading. To avoid this, there are 2 main ways data scientists measure distance in this context. Take the mean of the absolute value of differences. Absolute value is the function that replaces negative values with positive values. This is called the mean absolute difference, or L1 norm. Take the mean of the square of differences, which makes everything positive, and then take the square root, which undoes the squaring. This is called the root mean squared error, RMSE, or L2 norm. Important, it's okay to have forgotten your math. In this book, we generally assume that you have completed high school math, which means a lot of different things to a lot of different people, and remember at least some of it, but everybody forgets some things. It all depends on what you happen to have had reason to practice in the meantime. Perhaps you have forgotten what a square root is, or a square root is just the side of a square. So, yeah. So if you think of a square root is one of the sides, and the square itself is the area of the square. Or exactly how they work, no problem. Anytime you come across a maths concept that is not fully explained in this book, don't just keep moving on. Instead, stop and look it up. Make sure you understand the basic idea, how it works, and why we might be using it. One of the best places to refresh your understanding is Khan Academy. For instance, Khan Academy has a great introduction to square roots, and I love Khan Academy so much. The fact that I'm not spending more time on Khan Academy really disturbs me. I don't know why I'm not. But at some point I did actually put a really concentrated effort into just spending time on Khan Academy, because this is my will. My own personal will and volition mandates that I spend time on Khan Academy and learn everything here. But there are many cases where my will is hijacked, or I don't act in my best agency. I act in the agencies of others, and I don't spend time on here. But you can see there was a time where I spent a lot of time doing the math. They've since updated their curriculum, but I did get 100% through all of 8th grade math, which is so easy. I mean, it was just dumb busy work, but there was some stuff through 8th grade math, like statistics stuff, that I wasn't 100% in. A lot of geometry stuff I wasn't super in. But you can see I got through 71% of algebra, 61% of geometry, algebra 2, trig, pre-calculus, the statistics I got through a fair amount of as well. But you can see, look at this. It goes all the way up to linear algebra, and that's what is taught at the college level. So let's be very clear about what Khan Academy provides for free. It provides, if we're talking about social mobility and pulling yourself up by the bootstraps, that sort of thing, it's literally just a pure volition and an internet connection away. I spend time doing, looking at news and watching YouTube and not doing this. All right. So, oh right, I wanted to get all the way to the next section before I took a break.
Okay, so let's try both of these now. In both cases, the distance between R3 and the ideal 3 is less than the distance to the ideal 7, so our simple model will give the right prediction in this case. PyTorch already provides both of these as loss functions. You'll find these inside torch.nn.functional, which the PyTorch team recommends importing as F and is available by default under that name in FastAI, capital F. Here, MSE stands for mean squared error, and L1 refers to the standard mathematical jargon for mean absolute value. In math, it's called the L1 norm. S, intuitively, the difference between L1 norm and mean squared error, MSE, is that the latter will penalize bigger mistakes more heavily than the former and be more lenient with small mistakes. J, when I first came across this L1 thingy, I looked it up to see what on earth it meant. I found on Google that it is a vector norm using absolute value. So looked up vector norm and started reading. Given a vector space V over a field F of the real or complex numbers, a norm on V is a non-negative valued any function, P. V and then an arrow. I don't know what that arrow means. I know it's a formalized math term. I guess as it approaches, I have no idea. And then bracket 0, comma, plus infinity sign, end parentheses instead of end bracket. So there's an unclosed bracket, and it looks like there's also an unclosed parentheses. With the following properties for all A, E, I think that's epsilon, I don't even know, F, and all U, V, special character, uppercase V, comma, P, U plus V, less than or equal to P as a function of U plus P as a function of V. Then I stopped reading. I'll never understand math. I thought for the thousandth time. I mean, I understand it. There's no glossary for these terms. Since then, I've learned that every time these complex mathy bits of jargon come up in practice, it turns out I can replace them with a tiny bit of code. Like the L1 loss is just equal to A minus B plus AB.abs dot mean, where A and B are tensors. I guess mathy folks just think differently than me. I mean, they just like to formalize it, and they like to condense it down so that they don't have to write all this crap. You know, they can just write L1. I'm sure in this book that every time some mathy jargon comes up, I'll give you a little bit of code it's equal to as well, and explain in common sense terms what's going on. We just completed various mathematical operations on PyTorch tensors. If you've done some numerical programming in PyTorch before, you may recognize these as being similar to NumPy arrays. Let's have a look at those two very important data structures. Okay, and let's have a look at how much more reading I have to do. Oh God, yeah, see, I don't know if this is going to be possible. I have a very limited amount of time today. I need to watch another video. No. So I might be using this resource again. Yeah. So I'll leave that open, and I might need to come back to it. I mean, to be honest, like, this is just a better explanation than there was in the book anyway, so that's just going to be a good resource. Now, I will need to take that break that I've been saying I needed to take for the last half hour. I'll be back shortly. Alright, we got a red circle. We're going again, so let's go back and look at some of these questions here, because I know we got to the rank 3 tensor part. Here we go. So for pixel similarity, explain how the approach works to classify digits. The idea behind this approach was to look at all of the images for a given digit and compute the average value for each pixel across all images. Then, by comparing an unlabeled digit to that average digit, we could determine how similar or dissimilar the unknown image was to the known average. It almost sounds like pixel similarity just straight up is like finding a limit in calculus. Alright. What is a list comprehension? Create one now that selects odd numbers from a list and doubles them. Okay, well we can do that. So we're going to do pi-3-m I Python. Okay, and then we're going to create a list comprehension that selects odd numbers from a list. So we're going to say my list equals range 0, we'll do 100. Okay, so my list, okay, there we go. So now we're gonna select only the odd numbers. So we're gonna do a new list, and it's gonna be odd, or it's gonna be so we're gonna do number for number in my list if number divided by 2 equals int, because otherwise it'll be a float. Oops. Oh wait, modulus 2 does not equal 0. Okay, this should work. Yep, so now you can see we've only got the odd numbers, so I'll add that there. So we're going to say that it's shorthand list manipulation. What the hell? I heard like a weird like tin sound. It sounded like somebody flicked a tin can. And I don't have tin cans, but I do have glass jars, so I'm wondering if my glass jars got flicked somehow. I was wondering why there was like a flicking sound. But let's just focus. You know what? That's what these are for. So let's put them on. Oops, I think they're all backwards. Okay, yeah, that's not bad. So, okay, so right, list comprehension. So Python short hand for list manipulation, for creating lists. Okay, and then here's our list comprehension that satisfies the second part of this question. Okay, so And I think we already read about this. You know what? I think I'm just gonna abandon the book and I'm just gonna answer all the questions based on the answer list, because it's like, if they want me to stop and think about questions that led to a Nobel Prize, you know, I'm not sure if I can do that in a day. So let's instead of thinking about the questions, think about the answers. So what is the difference between tensor, rank, and shape? How do you get the the rank from the shape? Okay, so here's the answer. Oops. So a tensor's rank is equivalent to the number of dimensions a tensor has. Its shape is how many values exist in each dimension. Because the shape tells us the number of values per dimension, we can determine the number of values returned to determine the rank. Okay, so next part, what are RMSE and L1 norm? See, I'd love to do it the way they want to do it, but you know, I'm already an hour and a half in, and I need to do a whole nother lesson today, which has been taking me an average of like 6 hours. And I work full time, and I'm studying for the JNCIESP, and I juggle, and I swim. It's like, what is this going to do for me? What are RMSE and L1 norm? RMSE, or root square error, is the average difference between the prediction and the label squared and then second rooted. And there's a question mark. I'm not sure what that question mark is all about, but let's put that down as the first answer. Yeah, and we can get rid of that syntax there. Perfect. And then L1 norm is the average of the absolute value and the difference between y and y hat. Okay, so the whole thing just randomly freaked out on me. I don't know what happened. I've never seen this happen before. Oh, okay, okay. Yeah, when I tried to delete. Okay, there we go. There we go. Okay, that's not too bad. So maybe I can do like a. Nope, I can't. Okay. How can you apply a calculation on thousands of numbers at once, many thousands of times faster than a Python loop? Is that a list comprehension? Broadcasting. Create a 3x3 tensor or array containing the numbers from 1 to 9, double it, select the bottom right 4 numbers. Okay, well, I don't know how to do that. So let's go to the answer key. Okay, unfortunately, an exercise like that, they won't have like a code example or anything like that. I mean, I would use like pandas or something, right? I mean, the way I would do this without knowing what the answer is, you know, and just thinking about it by myself, you know, we'll see how that works for me. I would do this. So we'll say box equals 1, 2, 3.
4, 5, 6, 7, 8, 9. Okay, so now I have my array, right? Or my matrix or whatever. And then to double, I would say for I in box, and then for A in, or for J in I, then we'll say oh no. Yeah, we do for X, J in enumerate box, and then we do for Y, J in enumerate I, then we would do box X, Y equals J times 2. Okay, so now we've got everything in the array doubled. So that's what I would do, but is that the answer? Is that gonna work for me? Like, you know, if I think about it myself, one thing I've learned about myself is I'll come up with some kind of creative, unique solution that just is impractical or unusable and completely outside, you know, what the teacher ever imagined anyone thinking up. And it works, but like, is it practical? Like, is it gonna, like, and then not only that, I have to unlearn the solution I came up with because it's just so outside of the box and not what was expected. It's basically just like useless. Like, that's what I've learned about thinking through things myself. It's just that I'm too much of a kind of outside of the norm thinker to really do that effectively. But let's just go with that answer. I mean, I guess this is something I'd want to bring up in my discussion group. You know, I can even say that. Yeah, let's do that. Let's put this in the Discord and just say that I would like to discuss this. But yeah, that's definitely something I've learned about myself. It's kind of, you know, if somebody tells me to think it up myself, like, I'll usually come up with an answer, but like, it's typically not what I was expected to come up with. Especially when people ask me to do things that literally don't make sense and don't have a solution at all, and they were trying to trick me into like giving up or something. Okay. So to say, hey, even though this is from the lesson 3 questions, I would please like to discuss it on Monday. Oh, I shouldn't look at that yet because this is a private Discord. Okay, so what is broadcasting? Okay, broadcasting is traditionally used to support computation between two unequal tensor with the side effect of not needing to copy any data. This side effect can be taken advantage of for applying calculation to two tensors even if they are equal in rank. This needs to happen implicitly in PyTorch when operating of two vectors, for example, non-broadcasting, which is slow. Okay. broadcasting, which is fast. A tensor. Okay. Now, tensor is not. Yeah. So tensor is a thing that comes from a library. Yeah. Okay. Are metrics generally calculated using the training set or validation set? Why? I don't know. And I literally read like most of this, like a large part of it. Like let's see here, like well, probably not that much, maybe 1/6. But yeah, I prefer the thank you Thomas counts. You are doing a tremendous service to people like me who don't have 10 years to learn chapter 1 of beginning something or another. Are metrics generally calculated using the training set or the validation set? Why? A metric is a function that measures quality of the model's predictions using the validation set and will be printed at the end of each epoch. We use a metric to judge our network's ability to accurately predict outputs for data hasn't seen before. Okay, what is SCD? That's stochastic gradient descent, but I don't know much more about it besides that. Gradient descent is the process by which we update the weights, parameters, coefficients of our model in order to minimize the loss function. By taking the gradient/derivative of our loss function, we can determine how a change in our parameters would result in a change to the output. We can use that gradient to update our weights in proportion to the learning rate. Stochastic just means measure loss and update our weights in batches. Some definitions say that stochastic means we calculate and update for the entire training set. Okay, why does stochastic gradient descent use mini batches? We'll find that out. Oh, here we go. There's no hyphen in there. Updating parameters after every training example takes a long time and can mean sporadic jumps in parameters after each example as the network tries to optimize for each individual example. Waiting until after going through the entire dataset can be impossible for large datasets that don't fit into memory. It's inefficient and doesn't necessarily provide better results. Mini batches solve both of these problems. We reduce the variance between each parameter update and can smooth out convergence, and we don't run into memory issues waiting for the entire training to complete. Yeah, I'm on the final week of my 1 month diet plan to lose weight. And I wanted to cap my calories at 2,200, and I want, just me being just a regular old person. I just came up with a regular old person diet plan, but kind of as I've been falling into the rabbit hole more of nutrition and stuff, it seems like a lot of the science is pretty clear that like meat consumption, especially like every day red meat consumption especially, is like just absolutely not what humans are meant to eat. And I've been having 2 like grass-fed beef patties every day, and like I'm gonna be changing my diet on Tuesday to not be eating that anymore. And I'm just really curious how that's gonna make me feel, because I used to feel okay, and I still, feel pretty good sometimes, but I've been getting heartburn. I've been getting like, and today I've been having like pretty bad like chest pains, which is like never a good sign. Like I've never had chest pains like this before, so it's like, I just don't think eating that red meat is really a good idea, because I think I mean in health questionnaires at doctors' offices they ask you if you eat red meat, because I think it's pretty much known to science that humans are really not meant to eat large quantities of red meat, especially not daily. So I'm pretty concerned about my health right now with these chest pains. I've never had this before, and I I'm gonna be switching on Tuesday, but it's like, am I gonna even survive until then? I mean, the reason I'm bringing it up is because it's weighing heavily on my mind. Do I switch on Tuesday, or do I just, toss everything out now and immediately switch, or just, stop eating the beef patties? I've only got 2 days left. Actually, I've only got 1 day left. I'm going to stop eating them tomorrow, but I mean, I can't even be sure that it's the beef patties, and if I just stop eating them, I won't have chest pains and heartburn. I actually think it's more likely that the heartburn is caused by the tortillas, because they tend to correspond with when I eat the tortillas. So I'm pretty sure the heartburn has to do with the tortillas, but the chest pain is really surprising me today, and this is the first time I've ever felt chest pain like this, like in my life, pretty much. Alright, so what are the 7 steps in SGD for machine learning? So initialize weights, predict, calculate loss, determine gradient, update parameters, repeat, and stop is the 7th step, stopping. Okay, but let's give each its own letter. So first step, initialize weights, predict, calculate loss, determine gradient, update parameters, repeat is step number 6, and then stop is step number 7. Yep, so just like the musical scale, there's 7 different notes, and then the last note you play in a scale is just the first note but an octave higher. How do we initialize the weights on a model? Randomly. There are other methods, but randomly is a good starting point. What is loss? Loss is the function that tells us how well or how poorly our model predicted an output for an example. Why can't we always use a high learning rate? The learning rate is what we use gently. The learning rate is what we use gently. Let me put it this way.
colorless green ideas sleep furiously. That's what that sentence is saying. Well, it's actually saying the opposite of that. It actually is conveying some meaning, but the syntax is just completely broken. The learning rate is what we use. Gently adjust the parameters. A high learning rate can cause our loss to jump around sporadically as we attempt to minimize it. Okay, so what is a gradient? The gradient of a function denoted as follows is the vector of partial derivatives with respect to all of the independent variables, aka the parameters. The derivative, it's a function that describes the slope of another function at a given point. It tells us how quickly a function changes at a certain point. To calculate the partial derivative of a single parameter, you hold all other parameters constant. After computing all of the partial derivatives, they're collected into a vector called the gradient. Okay, so I think that's going to be it. Yep, we've got all the questions, so that's going to be the end of this video here. Oops, but we are going to do another video. So let me switch over to the correct Drive account. Perfect. Trash is changing. Okay, so we've got lesson 3 here. Lesson 3 had the questions just answered. So let's make a new folder for lesson 4. Okay, and then let's make a new file for the questions. Okay, so we've got a new file for the questions here. The next step we're going to do is fill that out with the questions for this next part. Okay, so this is going to be lesson 4. This is the lesson oh shoot, never mind. Lesson 5 is the ethics lesson. That's kind of the lesson I was looking the most forward to. But unfortunately, this is going to be another deeply technical and uninteresting lesson. But the good news is lesson 5 is only one lesson away now. Before it was 2 lessons away. Okay, so here's the questions we're going to need to go through. So I will see you in the next video where we will begin lesson 4.